All right, here we go. So today we're going to learn about power. This tends to be a pretty small sort of section on the AP test, so we're not going to stress about this one too much. So we're going to hit a lot of little basic ideas here, all right? So check it out. So power, hopefully you remember from honors, the power due to a force is the rate at which that force does work. I find that it's easier to think about it as the rate at which the force transfers energy from one form to another, okay? So if you want to calculate the average power, you're just figuring out how much work is done per unit time, okay? Now, if the rate at which the energy is being transferred is changing, then we need to talk about instantaneous power, right? And then that's going to require calculus. So it's the derivative of the work with respect to time, all right? Units. So because we're going to measure power in units of work per unit time, well, work is measured in joules, time is measured in seconds, so power is measured in joules per second, which we just call watts. All right, so 1 watt is the same as 1 joule per second. Okay. So I think this is probably easiest to see just by doing a few examples, all right? So we'll start out with the basic one, and then we'll work our way up to the calculus-y stuff. And then at the very end, I'll show you a trick and one other way to find instantaneous power. I don't mean a trick. I'm not going to like pull a rabbit out of a hat or anything. All right, so here we go. So first example, Roy lifts a 20-kilogram box up 3 meters in 4 seconds. If the box begins and ends at rest, then how much average power did Roy use? So what we're looking for is the power, average power, but specifically by Roy, right? So one of the things to be conscious of here is that Roy is a non-conservative force, right? So average power is it's the amount of work done per unit time, right? Specifically, we're looking for the work that Roy does per unit time. All right, and so again, it's important to note that Roy is a non-conservative force, and presumably he's lifting the box. He's the only non-conservative force. So this is equal to the work done by non-conservative forces per unit time. And hopefully you remember from our last section that the work done by non-conservative forces is just our change in total energy, or our change in mechanical energy, I guess I should say, right, per unit time, right? Now, if we're lifting a box and begins and ends at rest, that means the kinetic energy starts and ends at 0. So really, our only change in energy is GPE, right? So we're looking at the change in GPE per unit time, all right? Roy, as he lifts the box, is giving this box gravitational potential energy, and he's giving it some amount of gravitational potential energy per unit time. So this just becomes mg times the change in height per unit time. Which gives us, well, let's plug in our numbers. I'm totally out of room here. So this is, let's see, 20 kilograms times 9.8 meters per second squared times our height, which is 3 meters, and this is all done in 4 seconds. So if you multiply that, you end up getting 60, so you get, what, 588 joules is how much energy Roy gave the box, and that took him 4 seconds. So divide that, and you get 147 joules per second, also known as 147 watts. All right, now you got to be careful there. The symbol for W is work, but work is not, I'm sorry, try that again. The symbol for work is W, but the units for work are joules. So let's do this. This is a quick side note here. So quantity, units. So work is a W measured in joules, J. Power, P, is measured in watts, W. All right, so just make sure you don't get the 2 W's confused. Yeah, there you go. Okay, so that's a pretty basic example. It's we're measuring how much energy Roy gave the box per second. 147 watts, 147 joules per second. All right. So here we're going to go backwards. This is how much energy will a 60-watt light bulb use if left on for 12 seconds? Well, let's see, we're trying to find out how much energy. So we're sort of looking for a change in energy that's kind of like work, right? And we're given information, what is this, 60 watts? Oh, well, that's the power. And we know the time that's going to go by is 12 seconds. Oh, so I bet they just want us to multiply here, right? We know that power is work per unit time. That means that work is power times time, all right? Maybe a more intuitive explanation of this is this. What is 60 watts? Oh, a 60-watt light bulb uses 60 joules per second. So 60 joules per second times 12 seconds. Oh, I just used 720 joules of energy. Okay. So that one really is just kind of designed to help you see sort of what a watt is. It's not a great application of the equations. Really, that's more dimensional analysis, I guess. Stoichiometry, I don't know what you want to call that. Stoichiometry might not be the right word there. All right, let's see. So let's do another example. So in both of those last examples, we were talking about sort of average power, right? And even in the light bulb example, the power was constant, right? It always uses 60 watts. So what happens if it's changing? All right, so here we've got this object that's moving along a horizontal axis. All right, and the kinetic energy in joules is given by this function here. Let's write that out again. Kinetic energy of our object at time t is 4t squared minus 3t plus 8. And the question wants to know, what is the net power? Now, I will say, I wrote the word net here just to emphasize it. Usually books won't do this. Usually they'll just say, what's the power generated? Okay. And the assumption, I guess, is that it's got to be net power. All right. So what is the net power generated by the object at 2 seconds? All right. And notice it's describing an instant, right, at 2 seconds. All right. So now we're not talking about average power. We're talking about instantaneous power. So P, instantaneous power, is the rate at which work is done. Okay. It's the derivative of work with respect to time. So, but because we're talking about sort of net power, that means this is net work, right? Oh, but remember, the work kinetic energy theorem tells us that net work is the change in kinetic energy, right? So I can just write this as dKE dt, right? And I guess technically there's a little change in KE there, but the D and the delta tell us the same thing, so that's a little redundant. Okay, so in English, I want to figure out at what rate my energy is changing, right? Remember I told you that I like to think of power as the rate at which energy is transferred. And in this case, we're transferring kinetic energy. Okay, so I'm just going to take the derivative of the kinetic energy. So the derivative of 4t squared minus 3t plus 8. Make my t's look more like t's. So let's see, what does that give you? 8t minus 3. So that's my power. And so then at 2 seconds, I'm just going to plug in 2. So 8 times 2 minus 3 gives you 13 power. So it's got to be watts. All right. Okay. Quick unscheduled side note. Nope, never mind. Sorry, getting ahead of myself. Okay, moving on. All right, so this time we're going to go backwards. So this time, instead of giving us an equation for the kinetic energy, this time I'm giving you an equation for the power. So here we've got an object that's got a mass of 10 kilograms. It's moving along the horizontal axis. The net power in watts can be expressed as a function of time. So here's our equation for net power, 4t cubed minus 6t. So that's the rate at which we are transferring energy. Let's see. I know that at t equals 0, my velocity is 4 meters a second. And the question wants to know at t equals 3, what is the velocity? All right, so, well, let's see. So we know that, I'm going to swap colors here. So let's see. we know that net power is the derivative of work with respect to time. So this is going to be new to you, but once I tell you this, it'll be a new equation for you that you can use, all right? So those of you that are kind of calculusy know that we can integrate both sides of this, and it gives us this equation. The work done, I guess I should put a little net here. The work done is the integral of power with respect to time, okay? That's just integrating both sides of this equation gives us this, all right? And then specifically here, we're talking about net, right? Okay, so those nets don't have to be there for that equation to be true. Okay, so these are two equations. Power is the derivative of work with respect to time. That's a thing always. And work is the integral of power with respect to time. Also a thing. So those are equations. Put those, on your list of equations. All right. So for us, let's see, we're given this power equation. If I integrate it, that'll give me my work, specifically our network in this example, right? Which is our change in kinetic energy. Okay, so that's the path we're going to take here. All right, so let's let me clean up my board a little bit here. Let's rewrite all this stuff. All right, so here we go. So I know that my network, I guess I should comment here. I think in the last video I used this notation for network, right? So those are the same thing. So that's the integral of our net power with respect to time. So that's the integral, well, I probably want to integrate from 0 to 3 seconds, right? 0 to 3, 4t cubed minus 6t dt. So that gives me, let's see, the integral of 4t cubed is t to the 4th minus the integral of 6t is 3t squared, and then I want to evaluate at 0 and at 3. So if you plug in 3, you get 81 minus 27 minus 0, so you just get 54. Okay? So what I just learned then is my network is 54 joules. Oh, that means my change in kinetic energy is also 54 joules. Aha! So if I use this information, I can calculate my initial kinetic energy, 1/2 mv squared. Remember our mass, oh, it's right here. Our mass is 10 kilograms, right? So 1/2 of 10 is 5 times 4 squared times 16. So that's 80 joules of energy we began with. This is telling us we gained 54 joules, right? So if you want, you could do this. Change in kinetic energy is final minus initial. So what do we got? 54 equals KE final minus 80, right? So that means our final kinetic energy, in other words, our kinetic energy after 3 seconds is, if you add 80 to both sides, you get 134 joules. So that's equal to half of the mass times the velocity squared. Solve for your velocity, you get 5 points. I sat my paper down foolishly, 5.18 meters per second. All right. Cool. So let's take a quick second and recap. So what have we learned so far? So we've learned that if you want to calculate the average power generated by a force, whether it's net force or Roy's force or a non-conservative force, you take the work done by that force and divide it by the time. If the rate at which the energy is being transferred is changing, then you get the derivative, then you get that your power, so anytime it's just P, the assumption there is that it's instantaneous. All right, so that's the derivative of work with respect to time. And then just remember, work is about a change in energy. So this work might be the change in kinetic energy if you're talking about the net. It might be the change in total energy if you're talking about non-conservative forces. All right, so just keep in mind that those work, you know. No pun intended. All right, and then in our last example, we flipped this last equation around to see that work is the integral of power with respect to time. Okay? So, one last equation and example. So check it out. So, sometimes the power, the rate at which the energy is transferred is not constant. The power is not constant, but you're not sort of given an equation. All right, so let's go through this. The equation's already written up here on the board. I'm going to write it out again because I think I'll help you kind of follow what's going on. All right, so check it out. So power is the rate at which the energy transfer is changing, right? No, sorry. It's the rate at which work is done. It's the rate at which energy is transferred. I had an extra change in there. All right, now, we know from the definition that work is the dot product of force and displacement, right? So this is the derivative of force times displacement times cosine theta, right? I guess I probably should use delta R here, right? Since it's not necessarily along the x-axis, right? dt, right? Okay, but look, change in position per unit time is just velocity, right? So I'm going to rearrange some stuff, and there's a little bit of calculus weirdness that goes on here. So this is d delta r dt times f cosine theta. Notice here I'm assuming your force and your angle are constant, all right? So remember here that in this equation, this f delta r cosine theta, this guy here, in that equation, remember your theta is the angle between your force and your displacement, all right? So we're over here now. So it's the change in position per unit time times f cosine theta. Oh, well, change in position per unit time, that's just velocity. So that's velocity times force times cosine theta, or more commonly written, FV cosine theta. And again, theta is simply the angle between your force and your velocity vectors. Okay, so, and then sometimes you'll see that written as a dot product. Okay, so I would be really surprised if on the AP exam you had anything where this angle was not 0 or 180 degrees, but you should know how to deal with it just in case, because it does come up from time to time. All right, so again, if the power generated by the force is not constant, but the force is constant, I did not stress this enough the first when I wrote these notes up. All right, so this equation only works if your force is constant. All right, so in this example here, Roy pushes a 30-kilogram box across a frictionless surface with a horizontal force of 120 newtons for 5 seconds. So here's our surface, here's our box, 30 kilograms. Here's our force of Roy. This is all going to happen for 5 seconds. Notice my velocity is always going to be this way, right? So for this problem, our angle is 0 degrees. Because my force and my velocity are parallel. All right, so all right, so A wants to know the average power. Oh, that's just average power. That's what we already knew how to do, right? So let's see, A, average power. Stick to your equations. So we learned that average power is work done per unit time. And for us, we're finding Roy's power. Roy is a non-conservative force. Remember, work done by non-conservative forces is our change in total energy per unit time. Let's see, the only change in energy occurring here is our kinetic energy, right? So let's see, our initial velocity is 0, which means our kinetic energy initially is 0. Let's see. So at the end of 5 seconds, what's the velocity? Well, let's see. So acceleration, I'm going to use some old equations here. Acceleration is net force over mass. He's pushing with 120 newtons. It's 30 kilograms. So your acceleration is, what, just 4 meters per second squared, right? So after 5 seconds, the velocity will be 4 times 20, right? So Vf is Vi plus At, so that's just 20 meters per second. Notice I can only use that because my acceleration is constant. My acceleration is constant because my force is constant, which is going to buy us some stuff here later on. All right? So I know my initial kinetic energy. Now I can find my KE final. That's 1/2 the mass times the velocity squared. So that gives you 6,000 joules. So to finish part A, P average, we decided was our change in total energy per unit time. Because we're talking about the power from Roy, he's a non-conservative force, so he did 6,000 joules of work in 5 seconds. So that's 1,200 joules per second, or 1,200 watts. All right. Part B says find the instantaneous power after 2 seconds. Oh, so now we're talking about an instantaneous power. And I don't have a function I can take a derivative of. So now, because I'm finding instantaneous power, I can do this thing, FV cosine theta. All right, and the idea is Roy is exerting a force of 120 newtons. All right, and after 2 seconds, what would our velocity be? Well, let's see, it would just be 4 times 2, right? So 8. And then times the cosine of 0, all right? But so notice here, remember, work is force times distance. So that's newtons times meters, and then you're dividing by time, right? So the units do work out here, okay? It's force times distance. It's going to go 8 meters per second, so then you're dividing by time, right? So that gives you 960 newton meters per second, or joules per second. Right? So then when we do part C, power is force times velocity times cosine theta, but now our velocity is higher, right? Because in part C, we want the power Roy is generating after 4 seconds. So now my velocity, let's see, we're accelerating at a rate of 4 times 4 seconds is 16. So now it's 120 newtons worth of force being applied to an object that's moving at 16 meters a second. So that gives you 1,920 joules per second, or watts. I don't know why I didn't write watts. Watts. All right. So then D says, why is the power increasing? Well, the idea is so power is work per unit time, and work is force times distance. And so the idea is, as you go faster, you go a bigger distance per unit time, right? So down here, we were going about 16 meters a second, as opposed to only 8 meters per second. Okay, and as a result, you're transferring energy more quickly. All right, so that's D. And then E, how would the problem change if the force was exerted at 60 degrees below the horizontal? Then you just have to multiply all the answers by the cosine of 20. Okay. I think that's hopefully, obvious for B and C. Why is that true in A? Well, if our force was exerted at an angle, then only the horizontal component of Roy's force would be doing work, right? And so our net force wouldn't be 120, it would be 120 times the cosine of 60. So you'd end up with a smaller acceleration, and as a result, you'd gain less kinetic energy. All right, so that is that. So let's recap. So a minute ago, this was our recap, right? So the final thing that we learned then today is this, that you can also calculate your instantaneous power by taking the dot product of your force and velocity, which for us is usually just going to be FV cosine theta if F is constant. All right? So these are the 4 things that you should have learned in this video, with a little reminder of that. All right? Cool. How'd I do? 25 minutes. I'm trying to keep them short. I really am.